Hello, ma'am.
Uh, Good evening, ma'am. So we'll be starting
Good
right now,
evening, ma'am.
ma'am. Just with the intro.
Ma'am,
Okay, ma'am. We'll be.
actually, ma'am,
Yes, ma'am.
I have a query, ma'am.
Yes.
Ma'am, when will be the exam conducted?
After the third session today, sir, ma'am, at 6:30.
After?
The third session today, 6:30.
Okay, ma'am. And
It will be
when will
activated
we,
and it will be activated by
ma'am?
6:30. Yes, ma'am.
Okay, ma'am. Okay,
Okay.
from Atal account, ma'am.
Yes, sir.
We
From you
have
have
to
to
join.
log in the Atal account and there you have
Uh,
the. I'll show you the
we will get the
screenshot.
question from that
Yes,
Atal account. Okay,
yes.
ma'am. Another
I'll guide you.
question that
Yes.
when will we get the journal paper
Reflection journey.
or
We'll be
summary?
sharing shortly, ma'am.
Okay, ma'am. Okay, ma'am.
Okay.
Thank you
Okay.
so much,
Thank you.
ma'am.
Thank you.
Okay.
Thank you. So good evening, everyone. We will start the session right now. So welcome back again from TocH Institute of Science and Technology, and this is the last day. It's the day 6 of our FDP, and so we are so happy to have you all in the faculty development program sponsored by AICTE ATAL Academy, Next in Intelligence, HPC, Applied AI and Data Science. And it was being conducted from 8th December onwards. And we started with an inaugural ceremony by a eminent personality from Skylo, Finland, Mr. Anand Radhakrishnan on the day one. We had different sessions on all these days, starting with day one by introduction to supercomputing and AI by Mr. Praveen M. Vijayan. Session two, data science or data decision making by Mr. Sherry Thomas. And on the next day, we had the fundamentals of NLP and generative AI and continued with the unlocking the power of data and understanding the data science role in our industries and other activities by U2S. Day three session started with the emerging trends in AI and computing by Mr. Anishas Nair from Logic Space Technologies, followed by the session with along with hands-on on agentic AI by Dr. Sony P. Then we had the next session, and along with hands-on on object detection using single-shot algorithm by Mr. Lominjoy on day four. And on day five, we started with the LLMs and how LLM works, and then how to fine-tune LLMs, which was handled by Mr. Abhijit S. Pillai, who is a senior implementation engineer from 60 Technologies. And yesterday's last session, we had very interactive session with Dr. Chandan Karfa from IIT Guwahati on the applications of ML in semiconductor industries. Moving on to today's sessions, we'll be having three sessions today. The first one is the hardware for AI session, which will be handled by Associate Professor and Head of Research Lab, IIIT Kottayam, Dr. Kala S., followed by two sessions by our overseas experts, first by Mr. Jibin Jose from Netherlands and then by Jinesh Ahmed from Dubai. And over to the coordinators to welcome the resource person, and we'll start the session now. Thank you. Sarah, ma'am?
Oh, okay, sure.
Okay, yeah.
Is it audible?
Yes, ma'am. You can
Okay.
carry on.
Good afternoon, all. To the respected dignitaries, faculty members, researchers, and participants joining us for this online ADAL FTP. It is our great pleasure and honor to welcome today's distinguished resource person, Dr. Kala S., a highly accomplished academician, researcher, and leader in the field of VLSI and intelligent integrated system. She is currently serving as the head of the Intelligent Integrated Circuits and Systems Research Group at IIIT Kottayam. She obtained her PhD from CUSAT in 2020, did her MS from the Center for Nanoscience and Engineering, IIC Bangalore, and BTech in Electronics and Communication Engineering from MG University, Kerala. She is also a visiting researcher at the Chair of Embedded Systems, Faculty of Electrical Engineering and Information Technology, Ruhr University, Bochum, Germany, since 2023. Moreover, she is a recipient of the prestigious Weiser Award from the Indo-German Science and Technology Center in 2023. Her research interests span digital system design, system-on-chip design, VLSI and FPGA-based systems, computer architecture, intelligent systems, hardware acceleration of deep neural networks, and approximate computing. She has an impressive publication record in reputed journals and conferences such as IEEE, TVLSI, IACAS, VLSID, SOCC, APCCAS, among many others. And also, she is the winner of the Microchip VLSI Design Contest 2025 at the 38th IEEE International Conference on VLSI Design and has received several accolades, including Honorable Mention Award at VLSID 2023, Best Paper Award at IRTM 2021, and Best Student Research Forum Award at VLSID 2020. An active contributor to the academic and professional community, Dr. Kala is an IEEE senior member, a reviewer for several prestigious IEEE and international journals, and has served in key organizational roles for major IEEE conferences. Also been a keynote speaker and invited speaker at numerous national and international platforms. She is a passionate mentor, currently guiding multiple PhD scholars and undergraduate researchers, with her students receiving state and national level recognition. We are indeed privileged to have such a distinguished expert with us today. On behalf of the organizing team and all participants of this ATAL FTP, we extend a warm welcome to Dr. Kala S. and look forward to our insightful and enriching session. With great pleasure, I now invite Dr. Kala S. to kindly take over the session. Ma'am, please. Thank you.
Kala ma'am, you can share your presentation. You have been added as a co-host. Not at heard, ma'am. And,
Is it working fine right
yes, yes, ma'am. It is working fine now.
Yeah, okay. So I will not be using my microphones, yeah?
Okay.
Okay.
It's clear, ma'am.
Yeah, thank you. So I'll share my slides.
Yes.
Thank you, ma'am. Thank you for the nice introduction, and I thank Dr. Srila Sridhar, HOD of Computer Science Department, for inviting me to deliver this talk. So I'll share my screen.
Yes, ma'am. Your screen is visible, ma'am.
Actually, I'm not associate professor. I just wanted to mention that also. I have
Okay.
a cadre of associate professor till now. I'm waiting for the same. Okay, so my screen is visible.
Yes, ma'am.
Yeah. Yeah, sure. So the title of my talk is given as hardware for AI. Basically, by AI here, my focus will be more onto deep neural network accelerators for deep neural networks. So just to get brief of what I do in my research lab. So I'm heading a research lab, ASCAS is research lab at IIIT Kottayam. So basically we are working on an intersection of uh, AI and VLSI. So we are, our focus is mainly on developing the AI or ML algorithms onto, or implementing or deploying this AI or ML algorithms onto hardware or edge devices. So we work a lot on different kind of edge devices. So basically the broad area is edge intelligence. So when I say VLSI, it's not just VLSI, it's VLSI and embedded systems, because we deploy these algorithms, AI and ML, all these are very complex algorithms. These are getting deployed onto edge devices. There are different kind of edge devices. We will look into the different edge devices that we aim to deploy this AI and ML algorithms. So, yes. So I'm changing the slides. I hope that it is visible.
Yes, ma'am, it is visible.
Yes. So starting with just an introduction to email, I know that this is not required for this context, but still to have a flow of my presentation, I thought I'll spend few minutes on A and ML. As all of you know, we have this biological neurons, and then you mimic the brain activities of the brain to have this artificial neurons. So we have something called brain inspired computing there. So you take the you mimic the activities of the brain, so that you have what you say, artificially generated brain there. But so probably during yesterday's previous sessions, at least for Professor Chandan's session, you might have gone through this. I believe that because he also works on similar, we both work on similar areas. So at least you may have got an idea of how this artificial intelligence are mapped onto the real hardware, physical hardware, in your labs, or in your real-time app for your real-time applications. So here we have this fundamental units of brain, which are called the neurons. All of you may know this, but just to get the flavor of hardware, we will move through this basics also. So we have dendrites, axons, synapse, activation functions. This components are the constitute the basic building block of A. That is there are approximately 10 to the power 14 to 15 synapses in a human brain. And that, so the components of neurons are inputs. You have x1, x2, x3 denoted in this diagram, and then you have the weights w1, w2, wn, etc. Then we have bias, and then activation function. Basically this activation function, they'll decide whether the neuron has to fire or not. So next we have this spiking neurons. So spiking networks also, I think at least in some of the talks you may have heard about this. So this neurons are receiving these electrical spikes, and then these electrical spikes, here you have seen dendrites. So basically this dendrites will receive these electrical spikes, and then they are combined, all these electrical spikes from different dendrites, they have been combined together in a cell body. And then if this combined result, it exceeds a threshold value, then you know that the neuron will fire. So you get a spike there, and this spikes then will traverse through this what is called axons, and it reaches the synapse, and then this neurotransmitters are basically released, and then it will affect the next neuron, and that's how it traverses. So that is a spiking in computer. Basically, the spiking neural networks is a very hot area of research these days. It goes in both analog and digital side also. So coming to linear classifications, this is basically, all of you may be knowing this. This is fundamental machine learning techniques, and here the goal or the objective is to separate this data into different classes. Like we have a linear decision boundary here. For example, a linear decision boundary can be a straight line or a plane. It depends upon the 1D, 2D, 3D, or the dimensions. So linear classifier, it basically decides the class based on or using a linear function. So the linear function, you can see wx plus b, wx1, w1x1 plus w1x2 plus w1x3, it goes like that. So that is the linear classifier. But you have some limitations here. Linear classifier, it can, it classifies only if you have linear equations. For example, the very basic classifier is linear classifier is a perceptron. A perceptron is also or a neuron. Then you have something more as the linear classifier. You have what is a regression, logistics regression. Why this is linear? Because a boundary. The boundary is the decision boundary is linear. That's why, as you say, as you have seen. You can see here you have an input image, then you have stretched it onto the column, then you have this weights and then biases. So you got your classification results here. And if you graph this in two-dimensional, basically you have a straight line. If you go for a three-dimensional, it will be a plane. So if you go for higher dimensions, you have higher dimensional hyperplanes. So this is about linear classification. So you have some limitations here. Basically, this linear classification it works well for linearly separable classes. When the classes are linearly separable, this works well. But which means that you should have a meaningful linear relationship between these features. But when the limitation is that for non-linearly separable, you cannot go for this kind of classifications. Now we move on to deep neural networks. In that case, you can move on to deep learning models, deep neural networks, etc. So we are coming to that point where you have these neurons. We have seen this diagram in one of the previous slides. So we have the basic steps in the neural networks. You have this WIXI, weighted sum. Then you have activation functions, function of f of some z or whatever you call. You have this activation function. So different kind of activation functions we use. For example, we have sigmoid functions, ReLU, then what's the TANH functions, softmax, etc. So there are some interpretations here. So these weights are basically the synaptic weights or synaptic strength. And then you have a threshold value, as I said. So we call that threshold value is a bias here. Then you have this activation function, f of something function. So that function is basically, it decides whether to fire or not. So it's a firing behavior. And then you have this output also. The output, y is equal to activation of something you have written here. You can see that. So this output is basically, it is the spike that I was explaining in the previous slide. So it is an analogous to the spike or the activation level, whatever you call. And where do you have non-linearity here? The previous example, you have seen a linear models. Here in the non-linearity of this deep neural networks, who is introducing non-linearity to that? Basically, these activation functions. Activation functions are introducing the non-linearity to this deep neural network. So, basically, these activation functions, they will introduce some transformation. It's a function of. So it's a transformation function to this input data, and then basically this activation functions are pillars who will who's essential for this particular network, deep neural network, so that it can learn very complicated or complex patterns. Complex patterns you can learn using this activation functions. So this is an example of this is how the deep learning network, deep neural network looks like. So we will come to this computations in the neural network layers probably in another slide. And so the main point here is that non-linearity is which helps this deep neural networks to solve the almost all the real world problems and to learn complex patterns, because real world problems are typically very complex in nature. So here comes the non-linearity. So some of the popular DNNs, almost all of us know that you have fully connected neural network, which is also called that multi-layer perceptrons, MLPs, that we have studied. Then we have convolutional neural networks, recurrent neural networks, LSTM, a lot more are there. Graphical networks, graphic neural networks, so many adversarial networks, so many kind of networks are available for various applications. Now there are 2 points, terminologies to see here, that is training and inference. So basically training is the learning phase, so where this model will learn that patterns from the data. And what happens during the training is then you are giving some input data and you know the output or the labels, you know the data with the output also, and then it makes predictions, and then you will calculate the loss, the difference between the prediction, the actual output, and then you will update the parameters. So that is the weights and the biases, you will update that, and the ultimate aim is to reduce the loss. So typically it takes this training will take multiple days or multiple months or multiple hours, and you will require high power or powerful engines, GPUs, powerful machines, which has GPUs or a TPU, whatever is required in order to do this training. It's very time-consuming job. This training is very time-consuming. And then next you have the next phase, that's inference. So inference, this is basically in training, what you're doing is back propagation algorithm is running behind that, and for inference it is feed-forward computation. So the inference means the trained model. We have already a trained model with us. Those the trained model will, we are using it to make the predictions on a new data. So that's what you do in inference. So what happens during inference is that you are giving you give a new input to the model, and the model will perform what is called feed-forward computation. So basically, this inference is a computationally complex operation. Training requires more time, and memory is required. Similarly, inference is a computationally complex, basically feed-forward computation. We call it as feed-forward computation, and then you get the output of the predicted class or label or whatever value. And inference is the other point is inference is very fast when you compare it with training. So there are no weight updates or anything is done during inference, but during training you are doing the updation. So these are the 2 technical terms to be known. And why I was focusing on this is because when you take this AI onto hardware, we typically consider inference. Inference is a computationally complex operation. So inference will be, obviously training is also complex, but it's highly complex. Typically it's highly complex compared to inference, and it takes much time. So we do not take training on a hardware. We consider only a trained model to be deployed on a hardware. This is what we focus on. So when I say AI on hardware, when you see AI on hardware anywhere, it means that until and unless specified, it means that you are doing inference on the hardware. And basically the breakthrough of deep learning, it happened around 2010, between 2010 to 2015, the first 5 years, 2010 to 2015. It was possible because of 3 major components. So first one is computational power, then you have parallelism for training, which is availability of GPUs, and then availability of label dataset. Basically, you have powerful computational hardware units available with you. which is the GPU. Basically, that's the GPU. So that is one of the major breakthrough of deep learning during that time, a decade before. And due to GPUs, you know that you have this, and one more thing is that this machine learning operations or AI operations, these are metrics operations. You are doing, you have an image, you are classifying it, which means that you are working on a two-dimensional matrix, or you have a signal, you are working on a one-dimensional data. So whenever you play with images or frames, whatever, you are playing with the matrices there. So you have fast parallel matrix operations which can be performed on GPUs. And you know that training also of large for the large deep neural networks, it can be done in hours or days instead of months or multiple days. And you have availability of large data set. Why that why that matters, this availability of large data set? Because you have, if you have more data, you can have more generalizations, and then deeper networks, you can use a deeper network for training. And apart from these three, we have few more parameters, a few more, few more, what is that? Components which has enabled this breakthrough of deep learning. Such as you have multiple algorithms or novel algorithms developed, or better, better network architectures, neural network architectures have been developed for training and inference, etc. So that also contributed a lot. Every day you see new CNNs have been proposed. That also contributed. It's not just CNN, any deep learning architecture. That has also been that's a major point in the breakthrough or advancement of this deep learning. Now we will move on to, so here are some of the data sets, very popular data sets that has been used is shown. And now moving on to CNN. So the first CNN, basic CNN, that is LeNet, and then LeNet 5 architecture. So it has been proposed in 1998. So we will come to how do you compute this convolution, convolution dimensions, etc. in the next few slides. So next we have this AICTE in 2012. This has been proposed through that. That competition was the ImageNet competitions, and earliest one was the LeNet, which used this was used for a digit classification. Now, actually, almost all whatever modern CNNs are having right now, that has emerged from this LeNet convolution. Basically, the format is same. Template convolution is subsampling fully connected layers. Then you add more layers onto that. So AICTE here you have 5 convolution layers, then max pool layers, and 3 fully connected layers. So now we will see how do you compute the layers of AICTE. Even it's not just about AICTE, for any convolutional networks, how do you decide the parameters? How do you decide, how do you decide the parameters? In the sense, you have this numbers, right? Volume, output volume, input volume for the next stage, etc., etc. How do you compute that? So in AICTE, you have 227 by 227 the image size, input image size, and then you have RGB channels. So you have 227 by 227 into 3 images. And for first convolutional layer, you are taking, you are having 96 filters, 96 or 96 channels for the filter. The filter sizes or kernel size is 11 by 11. And the stride, so this is a convolution operation. So it's a windowing technique. You have the input image, you have this kernel size of 11 by 11. You operate on that in a window with a stride of 4. The stride is 4 here, there. Typically nowadays you see stride as 1. So AICTE was using stride 4 for the first layer. So how do you find the output volume? What is the output size for the first layer? So that is input image size, that is 227 minus the filter size divided by the stride is 4 here, plus 1. That's how you get that 55. So now you got the, after the first layer, you have output size 55 by 55. And you have used 96 such filters in the first layer. So you have 96 multiplied by 55 by 55 into 96 there. 96 such channels are there in the output feature map. So this is how you compute every layer. Each and every layer can be computed using this formula. So total number of parameters. So how do you find out the total number of parameters? So you have an input image here, 227 by 227 into 3. And you have a filter size of 11 by 11. 96 such channels are there, which are applied at the stride of 4. So you got 55 by 55 into 96. Now, how many parameters are there? How do you compute the parameters, number of parameters? So this is computed using the formula filter size 11 by 11 into 3 channels into 96. Into 3 is the RGB channel into 96. 96 numbers, such numbers we have taken, which is equal to 35K. So this is the number of parameters in first layer. Similarly, you can do this for all layers. So second layer is a pulling layer. So pulling layer, the filter size is 3 by 3. Electronet, they have used 3 by 3. And there the stride is 2. Instead of 4, the stride has been changed to 2 there. So output size is equal to input image size, that is 55 by 55. So 55 minus 3 filters. 3 is the filter size divided by stride plus 1. So it is 27. So you got 27 by 27 in the next layer. So you can see that here. So you can find out the parameters, number of parameters in each layer using this equation, this formula. So here it is given 27 by 27 into 96. Then the next is in normalization. You don't change the dimension there. So in convolutional 2, then it has changed. 256 such filters have been used. So into 256 came there, and then in convolution 3, 384 has come. Such numbers have come. So this is how you compute. Similarly, for VGGNet also you can do similar computation. So basically, this formula should be used whenever we propose a neural network. This is the formula that we are following to find out the size of feature map, how many numbers we should use, etc. Similarly, for VGGNet also we can do this operations. And now here, instead of the 11 by 11, AICTE has used very big numbers, filters. Here it is a very small number. And one more thing, why we are studying this small deep neural networks is because for when you deploy something on hardware, typically we always take smaller models because we may not have enough hardware to deploy bigger models. So we always look into or study in depth about smaller models only. That's why we start with LeNet and AICTE and VGG16, VGG19, probably ResNet 18 also. Mobile net or lightweight or yes, or lightweight models also we can look into when we deploy this on the hardware. Why we are using in VGNet, smaller filters have been used because you can get the similar output as that of larger filters using multiple and also you will get less number of parameters. Of course, if the number of parameters are more, you require more memory, you require more storage, or if you have more coefficients, obviously the memory requirement is more. And in VGGNet, these are the number of parameters. So when we look into hardware, we have to find out how many parameters are required to be stored, how many computations you require, etc. So basically, based on that only we can select the kind of hardware that we have to choose for deploying this particular model. So total memory. So here you can see convolutional 3, you have so much of 3.2 million memories and 36K. 36K parameters. So this is the most, it's the largest kind of, for convolutional 3, you have so much of parameters, then you can check down what is the largest size that is required when you implement VGG16. Typically, when you implement VGG16 on hardware, you are implementing one layer will be computed, and then the output of that layer will be given to the input of next layer, right? So it's a serial kind of computation. So maximum, which layer takes maximum memory, that will be the memory requirement of that particular deep neural network on the hardware. It is not like you are adding all the memory and that much memory is required, because at a time only one set of layer, one layer is computed. And when you compare convolutional layers with you have fully connected layers also here. In fully connected layers, what is the memory requirement? Sorry, number of parameters are more to be stored are more. But when you see computations, 90% or 90 to 95% of the total computations in a CNN will be performed by convolutional layers. But majority of memory requirement will be used by fully connected layers. This is the proportion. 90% will go to 90% of computation will go to convolutional layer. At the same time, maximum memory requirement will go to fully connected layers, because it is fully connected. You have so much of coefficients to be stored. Each neuron will have a connection with all other neurons. Now coming to hardware accelerators, moving on to so this is an introduction to CNN is over. So the topic is hardware accelerators for ML, hardware for ML. So what is this accelerator? First of all, the term accelerator. We will come to that probably in another 1 or 2 slides, I think. Yes. So you have some software to be accelerated. So what is the software? Software is the AI algorithm. You have a training, you have inference there. As I informed in the previous slide, that we are looking into inference to be implemented or deployed on the hardware. It's not the training, because you take a trained model and then implement it. So this trained model can be any CNN, or you can have RNN, transformer model, anything. It can be anything. You can implement any kind of machine learning or AI algorithms on hardware, but it is very difficult. It's very difficult to implement higher models on hardware. It can be implemented provided you have the adequate hardware with you. So our focus was on simple machine learning models and simple CNN models, deep neural network models. So what kind of hardware typically we use? We can have the typical conventional von Neumann architectures or CPUs. But when you implement an architecture on a CPU, we call it as a software simulations, which performs a sequential execution, And then apart from that, you can have, and we have NVIDIA's different devices from NVIDIA, which can perform. So here I can see NVIDIA Jetson Nano. In our lab, we were using NVIDIA Jetson, higher versions of Jetson Nano as one of the edge devices for implementation of AI algorithms on hardware. Then we can have another ASIC, application-specific ICs. Then you can have something called FPGAs. Here you see pink, Silence Alveo, all these are accelerator. This Silence Alveo is an accelerator card, which is very powerful. It's probably 15 lakhs or something. It's a very powerful device for implementation of any AI algorithms on hardware. Then you have pink boards. You see, these are like very light models. I mean, very light devices for implementation of hardware, AI algorithms on hardware. So, what is this hardware acceleration? Again, moving on to the title. So, so hardware acceleration, we have definitions for this hardware accelerated action or hardware accelerator. You can use some specialized hardware for performing some functionality, or you can use a specialized hardware for performing some functionality or a specific task or a specific computational task very fast or faster when compared to uh, a CPU. So you have a specialized hardware which performs some functionality. That functionality can be any computational task very efficiently, very or with high performance or with much efficient and fast with good execution speed. When you do the same on a CPU, general purpose processor, so that is called hardware acceleration. So, for example, you have a CNN. In CNNs, you know that who is the computationally complex area in CNN? It's convolution operation. So you take that particular functionality, that particular task, and implement that on the hardware. Specializing, you prepare, you come up with a hardware which performs that convolution operation. So when you do that on a hardware, you will get a better result when you compare that with the running the same algorithm, same functionality on a software. That is called hardware acceleration. So efficiency or performance, more efficiency you get on a hardware. So your comparison is with the GPUs, not GPUs. Comparison is with CPUs, general purpose processors, GPPs, general purpose processors or CPU. So yeah, instead of running everything on the CPU, what you do is you take some operations, some computationally complex operations on hardware. For example, some you know that CPUs are doing what is the sequential execution. So you have some algorithm, and which some part of this algorithms can be done in parallel. So why should you use the CPU? Instead, you can do this hardware, which gives you better performance. So those are offloaded onto some custom hardware units. That is called hardware acceleration. So what kind of hardwares you can use? In the previous slide, you can see then one human kind of architectures you can use, which is a conventional architecture. But instead of conventional architectures, you can also use unconventional form of architectures also. This unconventional form of architectures, that is, those are called neuromorphic architectures. You might have heard of this term, neuromorphic hardware. So that is basically it's a recent advancement. Probably 5 to 6 years, people are working a lot on neuromorphic architectures. You might have heard about this in some of the earlier presentations somewhere. Why are you deploying this on the hardware? First point is, why do you need a hardware accelerator? Because when you work with embedded system, embedded devices, obviously embedded devices, these are very small portable handheld devices. You have sometimes you will have to take it on the hand, right? Mobile phones, for example, mobile phones, these are embedded devices. So when you take it onto the hand, your hand should not be heated up, which means your energy, the power consumption should be very less. So when you use the GPUs and all, you know that neural networks will take 80 watts, 90 watts, etc. But when you take a specified, what is a domain specific accelerator, domain specific in the sense your domain is A, or a CNN acceleration, it's a domain. A deep learning acceleration, it's a domain specific accelerator. So if you take that domain specific accelerator or specialized hardware, you can save a lot of power. You can save a lot of power. In the place of 80 watts, you may be using probably 20 watts. So you save a lot there. So that is a power constraint. That's a power constraint of modern computers. So you have power or energy efficiency is very important in these modern days, and that's why. And also you have huge, large data available and large computation explosions. You have, as I said, you have multiple novel algorithms or AI models coming daily. So in that case, you should have a specific specialized hardware architecture to deploy that. So this is why you go for hardware acceleration. And moreover, your requirements are almost all real-time requirements, real-time processing requirements, which can be met using specialized hardware. Okay, so this is about specialized hardware. Then we will move on to need for speed. Yes. As you know, you have deep learning models which involve millions or millions or billions of parameters you have, and the operations running behind these are matrix operations, matrix multiplications. Basically, general element wise matrix multiplication is what we use inside this inference of deep learning models. And you have, it is recursive, repeated matrix multiplication. So, millions or billions of MAC units, multiplication and accumulate units are required. It's convolution operations are multiplication plus an addition. So it's basically accumulation, MAC operations. So, and CPUs are highly optimized for general purpose operations, which are basically sequential in execution, sequential tasks, and they are very slow for doing this parallel matrix operations. So there are specialized hardwares, as I said in the previous slide. You have GPUs, TPUs, FPGAs, field programmable gate arrays. Then you have neural processing units are also there. I missed to mention that in the previous slide. That is also there. Then and another point is that here you have big data available. You have millions and billions of parameters. You have billions and millions of MAC operations to be performed. And now, when you see the hardware, you will have large bandwidth requirements, IO bandwidth and memory, large memory bandwidth. Because of course, inside the device, you may not have enough memory to accommodate all these parameters. So what you will do is you will use an off-chip. We call it as off-chip memory or external memory. So every time you will have to talk with the external memory, take the parameters from or coefficients from external memory, come back to the chip, then go back to external memory. Frequently you will have to traverse between off-chip and on-chip memory. So in that case, your bandwidth requirements, memory bandwidth requirements will be very high. So you should have a very efficient hardware to manage this memory bandwidth. At the same time, every time when you go from on the chip to off the chip, you use a lot of power there. Power consumption is very high. So optimum use of memory bandwidth is required. Optimum use of memory and bandwidth, enough bandwidth is required to mitigate that. So as in this previous slide, you can see silent salvio accelerators. This is an accelerator card which performs a application. So these are very, the specification itself says that they are HBM, or they're HBM in the sense high bandwidth memory, HBM, high bandwidth memory cards. These are. So now one of the metric that you have to look into, one of the metrics that you have to look into when you implement is memory bandwidth. Memory bandwidth is what you have to look into. So
Sorry, ma'am.
When you have a specialized chips, it is very with very lower energy or with very higher energy efficiency, you can perform the operations. So that is what the need for speed talks about. Then this is a summary of this acceleration. So our ultimate objective is to run the network faster. That is, you have very good performance in terms of, we should have very good performance in terms of execution speed or latency, then energy. In terms of energy also, you should have more efficiency. And in terms of cost, area also matters a lot. How much area your chip is taking to implement this particular AI algorithm. That is also important for us. And now coming to the DNN operations. So you have, as I said, matrix multiplication is the major operation happening inside deep neural network. The key operation is dense matrix multiplication. This matrix into vector multiplication. And for each layer, this is repeating for each layer. And then that is feed forward operations. And then you have back propagation, which is a just for training part. For multiplication happens for feed forward computations, which is very expensive. This is a very expensive operations. This is very expensive operations. So we should have some optimization techniques to reuse the weights. Once the weights are available, you have to reuse the weights. You reduce the memory there. Somehow you have to reduce the memory so that you can save a lot of power. And then if you in activation functions and ways, you have a lot of sparsity, you have make use of or exploit that sparsity so that the dense matrix operations can be changed or converted to sparse matrix operations. So you can save a lot of power, energy efficiency, better energy efficiency, memory, etc. And in DNN, you have a lot of parallelism available. So when you see, as I said, one layer can be computed, and after that you go for the second layer. So within the layer itself, within a single layer, you can have multiple parallel operations happening, because you see multipliers within the layer, they are independent. The sums are reductions. Only layers are dependent. So you have first layers and second layer dependent, but within the layer you have a lot of parallelism to be exploited. So there is no data dependent operations within the layer that can be statically scheduled. So you save a lot of energy there. You get better performance there. We have to reuse all the filter coefficients, input image coefficients, etc. And now the another technique for another metric you can see is a precision. Another technique for reducing the hardware cost, improving the performance. Execution speed also. Improving the execution speed is reducing the precision. So when you implement an algorithm on the hardware, we typically choose a precision, arithmetic precision for that. When you see GPU, you know that this is a 64. GPU uses 64-bit operations. And your GPP, CPU also uses 64-bit operations. But majority of this classification problems or AI problems, they may not require 64 bits. Why do you want to waste your data width there? With 64-bit is basically double precision floating point. So instead of that, you can go for single precision, 32-bit, or even fixed point, 16-bit fixed point operations. If they can give good accuracy for this particular applications, we should not waste your data width there. With the similar accuracy, if you get the result, we should go for smaller precisions. It reduces a lot of energy, it reduces a lot of memory when you compare with 64 bits. See, for reducing the precision, so you can even reduce the precision of filter or the image size or both. You can have different combination of precision. If your image size is 16-bit, you can change the filter size. Filter precision to 10-bit probably. You get some other result, but you have to adjust with the precisions of the output also. So it all depends on how much accuracy your application demands. So here is some example for floating point, 32-bit, floating point 16-bit. So this is a fixed point 16-bit. It's not floating point. Integer values 8-bit, 16, 32, etc. The kind of accuracy that you get with different precisions. So typically, what I have seen is in almost all the majority of AI on hardware, they have used 16-bit. Majority papers have used, researchers have used 16-bit. 16-bit fixed point, and nowadays it has reduced to 8-bit. 8-bit is good and sufficient for AI applications on hardware. It gives a drastic change in your result also, performance also, with comparable accuracy. So here, mixed precision, as I said, you can use mixed precisions also. Some weights, here weights are 4-bit, activations are 16-bit. You can multiply, but you have to account for the rounding also there. Then accumulators use the 24-bit. So different kind of precisions can be mixed up and used. It saves a lot of it as in the published in the NIPS tutorial. So the summary of the precision is that we can have a good memory reduction, bandwidth reduction, power reduction. So it's always good to reduce the precision. With if your application demands that much accuracy, that's all. And the other point is that always, as I said, we can always reuse the filter coefficients, image input feature map coefficients, etc. So you reuse it, and always try to stay local. In the sense, maximum cache memories, local memories have to be utilized instead of going outside the chip to save it. If you one point, if you go outside the chip, the energy increases a lot. Energy requirement, power requirement increases a lot. Your access time, your latency, everything will be affected there. A drastic change in the power consumption will happen at the moment when you go outside the chip. And then we'll see some of the algorithms for implementing convolutional networks. Convolutions, they can be implemented. This is published in CVPR. Convolutions can be implemented using Fourier transforms, fast Fourier transforms also, FFTs. So what you do is, convolutions are basically kernel, and it is an operation between the kernel and the image, input image. So kernels, you take the FFT, fast Fourier transform of the kernel. And for image also, you take the fast Fourier transform of image. You multiply both, and then you take inverse fast Fourier transform of the output feature map. So this is how you perform convolutions using FFT algorithm. Basically, when you do this matrix multiplication, you know that if you do A into B, you should have a match of the dimensions, n by n into n by m, something like that. So you should have a match of matrix size. If not, we should be augmenting zeros to get a match of the dimension. So there's a limitation here in FFT based algorithms. This is very fast. Basically, this is very fast algorithm for convolution, but it is limited by the size, dimension of the matrices. So it is basically suited for if your filter size is 1 by 1 or 3 by 3, you should never go for FFTs. If your filter size is 11 by 11 for some linear extent, if your filter size is very big, it is good to go with FFT convolution. FFT convolutions, basically it reduces a lot of operations. Complexity is reduced a lot. It is shown in these tables, boxes. Indirect convolution is a direct conventional kind of convolution which uses windowing technique. So the number of operations, you have good savings in the FFT convolution, but later on people have come up with the different algorithms or optimization techniques in this. That is FFT overlap and add method, FFT cap, etc. I can look into these papers later. And then we have fast algorithms. Second one is Vinograd minimal filtering for convolution. So here, this Vinograd minimal filtering is a very old algorithm. It is already there, but people started using this algorithm for image processing. Deep neural networks in 2017-16, that period only. Here, you have an input feature map. You can see first diagram is input feature map. Then you have kernels. Again, this input feature map is divided into small. So how much time I have? 3. So input feature map is divided into small tiles here, and so the big matrix is divided into small tiles. Big image is divided into small tiles, and then you have the smaller filters also. You take these filters onto the tiles, and then you do the windowing operation. So basically, in a conventional method, what you do is you do not divide this into smaller subtiles or tiles. a big image is entirely taken as it is, and then you perform the windowing technique. So here you are dividing it into tiles and then compute the convolutions for each tile. This is what they are doing. So I will not go into the details of this. So you have some metrics here to see M by M, R by R. When you say if Vinograd minimal filtering, the output f of 2 comma 3, what does it mean? The 2 denotes m, 2 is the m by m, 2 by 2. It denotes the output. What is the size of y1 you want? That is 2 by 2. This is what it denotes. Then orange color, you see it's R is a kernel size, 3 by 3 kernel. Then what is your input? When you know what should be your output and what is the kernel size, you can find out what should be your input. This is the reverse, the reverse direction you have to calculate. So what it does is that you have an input image. So there you should do some kind of transformation to change that input matrix into some other form or transformed form. Then you have a filter. Filter also you do some transformation. So there are some formulas for doing the transformation. Then you get a transformed filter. Now you perform windowing operation between the transformed or input and transformed filter. Then you get a transformed output. So this is the computations behind this Vinograd minimal filtering. So I will skip these computations for the time, for the time being. We have we do not have enough time to explain these computations as such. When compared with the conventional convolutions, this Vinograd has good complexity, better complexity. So it is always better to use Vinograd algorithm for smaller filters, for operations involving smaller filters. Yeah, we divide the big one into smaller tiles and then perform convolutions. That's what they do with some kind of transformations. Basically, this Vinograd minimal filtering, it has been proposed from Chinese. There is something called Chinese remainder theorem. So from Chinese remainder theorem, this has been proposed. And the hardware complexity is very good when you see Vinograd minimal filtering algorithm. So we have done some extra. So all these studies have been done by us, our lab. So we have done some experiments to compare conventional or direct convolution, FFT based convolution, Vinograd based convolution for different tile sizes. As I said, tile size is very important. I mean, what is the tile size that you choose when you do this? This operations, the blue color, you have a tile size. Then green color, you got some other tile size there. So that tile size is very important in determining the performance of CNN. So why we were doing this is because you can do the convolution operation in different ways. So which method will gives you faster convolution on hardware? That was the problem definition. So we have tried out with the different kind of convolution algorithms and find out what is the execution time for different tile sizes, so that we can choose some tile size which is efficient, which is good for implementing AICTE, VGNet, or ResNet. For different CNN models, the tile size will be different. The reason is that your filter sizes will be different for different layers. Now moving to accelerator for CNN. So as I said, 3 different algorithms we have studied, and we have taken a case study for AICTE initially. AICTE has 11 by 11 as the filter size for first layer, for second layer 5 by 5, and then 3 by 3. So for 11 by 11 is a filter size, it's a very big size. Filter size is very big. Kernel size is very big, 11 by 11. So we have chosen direct convolution or conventional convolution to perform 11 by 11 filter size. And for other filter sizes, we have chosen Vinograd minimal filtering algorithm. What makes the implementation different is that typically in existing implementations, what they have done is they have a dedicated hardware for performing convolution operations or convolution layers, and there is another dedicated hardware or dedicated processing engine or processing elements for um, FC layers, which means separate. You have separate for FC, fully connected layers. You have a separate engine for convolution operations. So what happens is you may have some overlapping there also, but you do not have a what is a single hardware for doing both. So what we have done is we have combined everything together into a single hardware with resource sharing. Whatever resource you use for first layer can be shared with the second layer. The first layer will be using direct convolution, and then the rest of the layers will be using Vinograd convolution. And fully connected layers, typically they are general element based matrix multiplication. So we have thought about utilizing this general element based matrix multiplication or GEM architectures in Vinograd also, so that we can have same kind of compute resources in both Vinograd and direct convolution and fully connected. So we have come up with the utilizing an efficient GEM accelerator, general element based matrix multiplier accelerator, with some optimization techniques. So the best GEM accelerator that we have seen at that time was ISCAS in ISCAS 2018. There was a GEM accelerator. What we have done is we have done some modifications in that GEM architecture with some blocking techniques, some techniques called blocking. Block multiplication. Some techniques called block multiplications have been used, and then we have generated or we have developed proposed processing elements for this GEM accelerator, which can be used to implement direct convolution or conventional convolution, then Vinograd convolution and fully connected layers. So this is a blocking technique. So basically what blocking technique does is you have a matrix, you divide that into submatrices and then perform multiplication. So data dependent, independent multiplications you can do there. And we have developed this architecture, blocked Vinograd minimal filtering algorithm, where you have the input data, you transform it using the transformation techniques. Then you have filter, you transform it using transformation techniques. You multiply both the transformed matrix and transform filter. You get some output and then take the transformation again. So, and the multiplication is block matrix multiplication. The multiplication that we have used is block matrix multiplication. So it is blocked Vinograd minimum filtering algorithm. And a lot of experiments we have done in order to choose what is a tile size. It was a very big design space exploration. And then we have come up with this unified Vinograd GEM architecture. This has been implemented on FPGA, Vertex 7 FPGA. So here what happens is, whenever you want to have a direct convolution, you can use the blue color lines. Whenever you want to use Vinograd convolution, you can use the red color data path. The rest of the data paths are same for all. So you have the choice of using either conventional or Vinograd for any layers. You can do one layer one by one. The layers are implemented one by one. So this is the architecture, and in the paper is available in Algebraic transactions on VLSI. So as I said, we have experimented with different tile sizes for AlexNet. Similarly, we have done this for BGG16, ResNet 18 also, and implemented that on the hardware. And a comparison have been done. And this work has got some award in VLSI Design Conference also in Bangalore 2020. And now moving on to sparse. So till this, we were dealing with dense matrices. And now the next work, it deals with sparse CNN, because nowadays we typically people have almost stopped doing dense operations on hardware, because if you have you can exploit the sparsity in the matrix operations in the real world problems. So what is sparsity? What is sparse matrix? Basically, most of the elements in the matrix, if the matrix has most of the elements as 0, you call it as sparse matrix. So there are a lot of real world problems which has sparse matrices components. Social, almost all social media, social networks, neural networks, in graph theory and all, you see a lot of sparse connections. Natural NLPs, robotics, so many operations are there where you use sparse matrices. So our next research was implementing sparse neural networks on hardware. So when we do this matrix operations or matrix multiplications on dense matrices, whatever we have seen, those kind of operations will not work on sparse matrices. You have a separate storage format for storing the sparse matrices. One of that is coordinate technique. So you have different techniques for storing sparse values, sparse matrix values. So one technique I'll say here. So you have coordinate operation here. So you have actual matrix 1, 0, all this matrix, and now wherever you have non-zero elements, you are writing that in the first as the value, the first row. You see the values have been written there, and then write the row index for 1. What is the row index? And for 1, what is the column index? Column index is, so it is 0, 0. Similarly for 7, it is 0, 1. So like that, you write the index, row and column index. That is coordinate matrix format. Similarly, there are some more. Another one is compressed sparse row. Here also, you make a modification to coordinate, and then you have another format. Then you have compressed sparse column, CSR, CSC, COO, CSR, CSC. These are the very popular format for sparse matrices. It's not just these 3 techniques. These are very popular, and apart from that, you have blocked CSR, delta CSR for different applications of different kind of patterns. You have patterns of sparsity. You have different kind of storage formats. So we have done a study of different sparse matrix storage formats, and then we have come up with an accelerator, a sparse matrix multiplication accelerator, which uses configurable tiling techniques. So we have combined a lot of optimization techniques here. And then we have called just MOSCON, modified outer space configurable accelerator, matrix multiplication accelerator. And this what this architecture performs is performs matrix multiplication using outer space product. It is another established technique for implementing multiplications. So this work also has been presented, and it is one of the best paper candidates at 2023 VLSID conference. So this work is it's a work of my PhD student, Noble, who is about to graduate within a few months. So what he has done is basically as I said, different matrix compression formats are available. So we have also proposed a novel matrix compression format for better efficiency in terms of area or memory efficiency, and you should be handling the irregular sparsity. Can be irregular, etc. So any kind of sparsity should be handled, and better deployment on the hardware should be done. So we have come up with another kind of sparse matrix format. So that is called a modified delta CSR compression format. Modified delta CSR compression format. Or it's basically memory efficient. It's a delta CSR is already an existing format, so we have modified it and made it memory efficient. So this work is recently we have published this modified or memory efficient delta CSR technique in IEEE Embedded System Letters. You can go through this paper. Details of this compression techniques available in the paper. It's a compression format. So when you have a CSR, when you have a normal metrics, sparse metrics, which is represented using CSR form, how do you convert that into memory efficient delta CSR format? And when you compare with this conventional techniques, we are gaining a lot of at least 15 percentage to 30 percentage of memory efficiency we are getting in terms of coefficients storage. And for various sparsity levels, um, for various sparsity levels, we have done experiments. A sparsity level less than 50, you can see, then between 50 to 60, 60 to 70, so many experiments we have done. And compared the compared our performance with existing techniques, and it has seen that CSR no, MDCSR compression gives better efficiency in this format. The paper is available. It's a very recently published one in IEEE Embedded System Letters, and this work has been presented in Embedded System Week in as a very prestigious conference, Embedded System Week in Taiwan. This work has been presented there. So with this, I am trying to conclude the talk. Before that, so now we have come up with a format which converts CSR to MDCSR, and we have done a few more work in continuation with this. And since those papers are under consideration for publication, I did not present it here. We have developed a sparse neural network, and we have done various different AlexNet, VGG16, mobile VNet, different kind of models we have implemented using this technique, and has been verified with almost all existing sparse neural network accelerators. We have seen comparable improvement. We have seen comparable improvement in our implementation. And this is a work done by my PhD student Nobleji, and this will be continued. This is going to be continued by another PhD student, Aparna. And this work, it is supported by Indo-German Science and Technology Center, DST, funded by DST and BMBF. So with that, I conclude my talk. So I would suggest you to go through our website of AICTE Research Lab, where we have given the work that we are currently doing, the research that we are currently doing. So apart from this is just one part of our research. Apart from hardware accelerators for AI and ML, we have been doing approximate computing, neuromorphic architectures, which is an unconventional architecture, hardware security. A lot of hardware security IPs have been developed in our lab, and then edge intelligence, edge computing. So in edge computing, we work a lot on NVIDIA Jetson and other devices, and we are always open for collaborations. You can reach out to me or I2CS at IITKottayam.ac.in. We'll get a response there. And I am extremely thankful to Women Involvement in Science and Engineering Research WISER program of IGSTC. It is established by DST and Government of India, BMBF, for supporting this work and supporting our foreign travels to Ruhr University, Bochum. So from Ruhr University, Bochum, we have Professor Akash Kumar, who is chair of embedded systems at Ruhr University, Bochum, Germany, and Dr. Salim, who is also with Ruhr University, Bochum, and Dr. Nalesh with QSAT, Kochi, who are collaborating in all the works that we have discussed here. And I am also thankful to my PhD students, my BTech undergraduate students, and my research assistants, research associates who have been, and my colleagues who have been supporting me and my lab for all the research that we do at IICS IIT Kottayam. So with that, I conclude my talk. Thank you once again. Thank you, TocH Institute of Science and Technology, for inviting me to deliver this talk. Thank you uh, to Dr. Smila Sridhar, HOD of CSC, for the invitation. I'm open to questions if you have any.
Thank you, ma'am. Participants, if you have any queries, you can ask now. Ma'am, I hope the presentation is over. Shall we switch?
Yes, yes.
Okay.
So I'll stop sharing.
So participants, is there any questions?
If you have any questions, you can reach out to me in the email also later.
Any queries from the participants? You can type in chat box also. And there is a question like how to determine the optimal number of hidden layers and number of neurons.
From a hardware perspective, or if it is from a hardware perspective, it is based on the availability of the resources that we have in the hardware. Because if you have so many layers, I am talking from the hardware perspective. Okay, hardware for A. If you have so many layers with so many parameters, your hardware may not support it. That's why I was discussing about very smaller layers. Initially, as I said, we start with LANet, AlexNet, VGNet, ResNet 18, even ResNet 50 may not support. ResNet 50 may not support on a hardware. Whatever hardware was available with us, we could not do very bigger models. And if the number of parameters increases, we don't have the memory, enough memory to save the coefficients and the resources, computational resources that we have, LUTs, lookup tables, DSP blocks, digital signal processing blocks, because these are MAC operations. You will require DSP blocks. So if your model is very high, we are not able to do that. So we have chosen pre-trained models basically. It was not like we were developing our own models. So that also we have done. We have developed our own models with the 2 layers, a single layer, etc. So that was again based on the availability of the resources that we had. Since our objective was to deploy this neuron on hardware, we have always chosen a minimum number. Minimum number is what we have chosen. If you have good accuracy, enough accuracy, or 75 to 80% accuracy, which is okay for certain classification operations, we have chosen minimum number. It was not like optimal number. It was not like an optimal number. It was like minimum number that we have chosen. If it was a customized, customized deep neural network. Otherwise, the pre-trained model is what we have taken so far, because training was up to GPU, right? So we don't play with training there. We don't play with GPUs. So whatever is available on the hardware, based on that, as minimum number has to be taken.
Okay, thank you, ma'am. So if there are no other queries, okay, how to raise the LLM? how the rise of LLM and generative AI influence the demand of underlying hardware infrastructure.
Yes, a very nice question because we are currently looking into LLMs. So one of my PhD student, it's very nice question because recently in the past 4 to 5 months we were looking on to LLMs. We have a project we have a project running right now which is in collaboration with the Vaidyaratnam Ayurveda Institute in Kochi, in Thrissur. There we basically it's a hair classification project. So there what we have done is we have it's again multimodal classification, multimodal processing. So we have combined vision task and LLM, and we have implemented deployed that on Jetson Nano. Basically, the hardware that we have used is even we tried with Raspberry Pi. Raspberry Pi is a very small device. Even the high-end Raspberry Pi could not, it can run LLM. We tried LLM, but it got heated up and switched off. It got heated up and switched off the Raspberry Pi, so we could not do that. So we tried with Jetson Nano higher version, some 75,000 baud is available. So we tried doing LLMs and vision tasks combined together on Jetson Nano. It was working perfect. It was working perfect. That was a PhD work. One of the PhD student has done, and the hardware right now we have enough hardware to perform LLM also. It was not FPGA, but it was NVIDIA Jetson.
Okay, thank you, ma'am. Sorry, ma'am. Any other questions from the participants? If not, I think the coordinator can wind up the session.
On behalf of the Department of Computer Science and Engineering at TocH Institute of Science and Technology, and from the side of participants who are present in this session, I wish to express our sincere gratitude for your outstanding session on hardware for AI during our AICTE ATAL sponsored faculty development program. Your expertise and insights truly captivated the audience. Your session on deep learning and its components really helped us to understand the practical aspects of how does an DNN works. Introducing us to some algorithms for CNN will help with our research, and it will boost our knowledge as well. Incorporating motivational techniques you have implemented in your own project as an example is really motivating and informative. It will truly help us with our research and building our own models. Thank you once again for sharing your valuable time and knowledge with us, ma'am. Your contribution was instrumental in the success of our FDP. For the entire participants who are present in this session and for the Department of Computer Science and Engineering at TocH Institute of Science and Technology, we would like to express our token of appreciation in the form of a virtual memento to you, ma'am. Please accept it.
Thank you. Thank you so much.
Thank you, ma'am.
Thank you, ma'am, for joining.
Yeah, can I leave now?
Yes, ma'am.
Thank you. Thank you so much.
Coordinator, you can stop the recording and restart it for the next session.